welcome to 21st lecture on ECD. In this lecture, we will start studying operational amplifiers. The operational amplifiers, we also call them op amps. Op amp, op amps. So op amps is a linear integrated circuit in contrast to the discrete components that we have been studying like transistors, diodes, and resistors, etc. This means this is an IC package, a plastic, mostly in a plastic casing, where we have a number of transistors packed into it. So operational amplifier we call so-called op amp is one of the simplest linear ICs we use in electronic devices and circuits. Right, the symbols and terminals are this is the symbol. We have a negative terminal and a positive terminal. The negative input terminal, we call it inverting input. The positive one, we call it non-inverting input. So here we apply input. We have two input terminals, and later we'll see that why do we have two input terminals and what are the applications that we can achieve or we can address using these two different input terminals, and of course one output terminal. And generally it is biased with a dual power supply, plus V minus V. This is the biasing voltage. So we need a positive battery as well as a negative battery. So ideal op amp circuit is a circuit that has infinite voltage gain, can work for all possible frequencies from just above 0 Hertz to infinite Hertz, has a very large input impedance, ideally infinite input impedance that is required so that it may not load the preceding stage, the stage that is driving it, and it has zero output resistance so that there is no voltage drop within the output resistance and the full output voltage is delivered to the load. So these are the ideal parameters that an ideal op amp should have, but practically it achieves these requirements fairly well. Infinite is replaced with very high voltage gain, very large bandwidth, very high or very large, very high or very large. So very high voltage gain, very large bandwidth can work for a very wide band. Right, and infinite input impedance means very high input impedance. So practically these three quantities are very large bandwidth, very high voltage gain, very high input impedance, and zero means very low. So the output impedance is very low. This is how we can draw it graphically, that Cin is zero, the output resistance is zero. This is replaced with a short circuit. So short circuit. And AV is infinite, C out is zero, but practically the Cin is very large. The input impedance that we see between the negative and the positive input terminals, this AVVin is very large, C out is very small. So practically we achieve these infinite and zero values with very high and approximately equal to zero or very low values. Right. So the block diagram of an operational amplifier is this. We have one differential amplifier stage, that is the input stage. The next stage is the voltage amplifier, where we achieve a fairly large voltage gain, and the output is a current amplifier based on push-pull combination that we studied previously in this course. So we have these three stages. We call them input stage, followed by a gain stage, and finally the output stage, that is actually a current amplifier. This is a voltage amplifier. This stage is a current amplifier. So what does a differential amplifier, the first stage, what does this differential amplifier refer to? This is actually a circuit that is based on two transistors Q1 and Q2. They're connected such that the emitters are connected together and they are connected to the negative power supply. We call it negative VEE through a resistor RE, whereas the where the collectors are connected to VCC through collector resistors. So now we have two inputs, input 1, output 1, input 1, input 2, two outputs, output 1 and output 2. So let's see how it works when both inputs are grounded. So the first mod can be when both the inputs are grounded. If it is grounded as well as this one is grounded. So what happens then? What happens? Since this is a negative voltage, negative VE, the space emitter junction would be on and there will be a current flowing between base and emitter for Q1 as well as for Q2. So there will be a base emitter voltage drop approximately equal to 0.7 volts, and there will be equal IEs and ICs flowing, and the voltage drop, if RC1 and RC2 are matched, they are equal, and the transistors are also matched, we'll have equal voltage drop. Since the collector currents for both these transistors are equal, so we'll have equal voltage drop. The voltage drop across RC1 would be the same as the voltage drop across RC2. So the voltage here, output 1, would exactly be the same as output 2. So if we measure voltage between these two outputs, we put a voltmeter here. If you put a voltmeter here, such that we connect the red lead here and the black lead here between output 1 and output 2, we'll get exactly 0 because the magnitude of these two voltages is exactly the same compared to ground. So this is one of the three ways we can use this differential amplifier, and this mod is called common mod because we have applied equal voltages on both input terminals. It's common mod. Input and outputs, they both are grounded. The other way in which we can use this differential amplifier is when input 1 or input 2, any of these two, is connected to a small voltage and the other is grounded. We call it single-ended mod. Suppose we have a small voltage here. The voltage here, maybe it is equal to, this voltage is equal to maybe 0.1 volt, right? And this is ground. So this voltage is 0.1 volt. This means now it is raised to 0.1. So the base emitter junction, this voltage VPE would be slightly larger than 0.7. So it would be slightly larger. The emitter voltage would be slightly increased, and that would take it more towards saturation, and the IC for this transistor will increase. The IC for this transistor will increase because this base emitter voltage is a bit larger than this base emitter voltage. Since the emitter voltage is constant, the emitters are constant, so we'll have a constant voltage here. This voltage is slightly larger than this voltage. The magnitude here is 0 volts. So this base emitter voltage, since the emitters are connected together, we'll have only one voltage at the emitter transistor Q1, the same voltage at this emitter as well as at this emitter. So VE1 would exactly be the same as VE2 would be equal to VE. So if we settle ourselves to a VE that is slightly larger than the VE that we had in common mod configuration, this voltage difference would be larger than this voltage difference. So whatever is VE base emitter 1, VBE1 would be slightly larger than VBE2. This will cause a VBE1 would be slightly larger than VBE2, this voltage, because the base is at a slightly larger voltage. So that will cause a larger IP flowing into the base of Q1 compared to the IP that flows into the transistor Q2. So that increased IP would cause an increased IC. So IC would also increase. So IC1 would be larger than IC2. This means the voltage drop across RC1 would be larger because IC1 is larger. That will cause a voltage drop across RC1 larger compared to the voltage drop across RC2. So V across RC1 is larger compared to V across RC2. This means the voltage here V output 1, V out 1 would be smaller than this voltage because a large proportion of the voltage is dropped here, or the voltage drop across this resistor is larger compared to the voltage drop across this resistor. So if this drop is larger, the voltage available here would be smaller. So we'll have a small voltage here, a large voltage here, and the difference would be non-zero. So in this case, when we have base of one transistor slightly at a higher voltage compared to the base of the other transistor, we'll have a non-zero output, a differential output. We can also do it otherwise, like we can connect the base of Q1 to ground and the base of Q2 to a slightly higher voltage. That would also result in the same difference, but with the opposite polarity. So we call it single-ended mod because we have applied input to any of the two inputs, either to the base of Q1 or to the base of Q2, and the other base is grounded. So let's move on to the last mod that we can use this differential amplifier in, is when both inputs are applied non-zero but different voltages. This is actually an extension of this mod where we have connected one base to ground and there to a slightly higher voltage. In a differential mod, it's actually an extension of a single-ended mod. In this configuration, we apply a voltage that is larger than maybe 0.1 volt. Maybe we apply 0.2 volts here. So the input voltage that we apply to the base of Q2 is slightly higher than the voltage we apply to the base of Q1. Of course, once again, since the emitters are connected together, VE1 would exactly be the same as VE2. So they will settle at a VE, at 1 VE, the same VE. Since this voltage difference VBE2 would be slightly larger than VBE1. Why? Because the base of transistor Q2 is at a slightly higher voltage compared to the base of transistor Q1. So VBE2 in this case would be slightly larger than VBE1. That means that the IB that flows into the transistor Q2 IB2 would also be a bit larger compared to the current IB1. So that will cause a greater IC. So IC2 would be larger now compared to IC1. So in this case, IC2 would be larger. Now IC2 is larger. This means the voltage drop across RC2 is larger than the voltage drop across RC1. Or in other words, the voltage that we find here at Vout2 would be smaller because this voltage drop is larger. This means the output voltage would be smaller. So this output voltage would be smaller compared to this output voltage, and we again have a non-zero output, a differential output between the two output terminals, output 1 and output 2. So this is how we can use this differential amplifier in these three modes: common mode, single-ended mode, and differential mode. We'll talk more about differential amplifiers in our next lecture, ECD32. Thank you. That's all for this. Thank you very much.